I work in the Ashton Graybiel Spatial Orientation Laboratory at Brandeis University, which means I get to work with all kinds of amazing machinery. One of the coolest things I get to work with is the lab's rotating room. Here's a simple model of it to help me explain some things to you. Once the room is spinning, we'll examine two different situations. First, we hold a ball still in the room and let go of it. Not so interesting when the room is still. Second, we throw the ball across the room, aiming for the opposite side. The room is 22 feet in diameter and it can rotate at up to 40 rotations per minute, but here I'll just show 10. We use the room to study human perception and adaptation in unusual force environments. We also use it to study the feasibility of using rotation to create artificial gravity for long-duration human spaceflight. Here on Earth, we can create that artificial gravity which pulls you toward the walls of the room, but we can't get rid of Earth's regular gravity. So usually, we stand on the floor of the room leaning inward. But in outer space, the walls would be the floor. The reason artificial gravity is important is that long-term exposure to weightless environments has severely detrimental effects on human physiology. Now let's put a ball in the room and pretend there's no Earth gravity at all, just because that'll be easier for us. At first, we'll hold on to the ball at about halfway between the center and edge of the room. As you saw, in a normal stationary room, the ball just stays put when we let go of it. But in the rotating room, the ball is already in motion when we let it go. It's traveling around in a circle. Sir Isaac Newton taught us that an object in motion will stay in motion until acted upon by an outside force. So when we let the ball go, it will just travel in a straight line until it reaches the wall, as shown here. Now let's try matching the camera's movement to the room's movement. As the camera starts revolving, the room appears to slow down, and the path of the ball appears to start curving. Now the room appears to be stationary, with the world spinning around it. So in this frame of reference, the ball is stationary when we're holding onto it, and it follows a curved path when we let it go. From within this rotating reference frame, it seems like Newton's laws aren't quite right. That is, unless we start talking about some extra forces that don't exist in the external, stationary environment. It will take two such forces, in fact, to satisfy Newton's laws in this spinning room. The first one you've probably heard of, centrifugal force. The centrifugal force on an object depends on where it is in the room. At the very center, there is no centrifugal force. The centrifugal force increases the farther you get from the center. Since this ball starts out away from the center, centrifugal force explains why it starts moving as soon as we let it go. But if centrifugal force were the whole answer, the ball would still travel in a straight line. A second force is required to explain the curved path we're really seeing. It's called Coriolis force. And unlike centrifugal force, Coriolis force doesn't care where in the room an object is. It only cares how fast the object is moving, and in what direction. If the object is still, it feels no Coriolis force. But the faster an object moves, the stronger a Coriolis force it feels. And the direction of the Coriolis force is always at right angles to the direction the object is traveling. What that means is that Coriolis forces can't actually speed up or slow down an object. They can only change the direction of the object's motion. And sure enough, when we let the ball go, it starts out as though there is only centrifugal force, because it starts out not moving. But as the centrifugal force makes the object pick up speed, the Coriolis force starts to kick in, changing the direction in which the object moves. And that's what makes its path curve the way we're seeing. Of course, from the external frame of reference, it's still just traveling in a straight line. For that reason, some people call the centrifugal and Coriolis forces fictitious forces. But when you're inside the rotating room, they feel very real. If you move your arm, it will be deflected unless you can provide additional force to counteract the effect. Einstein's theory of general relativity says that gravity itself is actually the result of an accelerating frame of reference. So in a sense, gravity is equally fictitious. Now let's start the ball at the edge of the room and actually throw it. Keep in mind that, in the external reference frame, the ball is already traveling in a circle around the edge of the room. So if someone throws the ball the way they normally would to make it fly straight ahead of them, the contribution of that initial speed will cause the ball to fly away from them at an angle. But once it leaves their hand, it will continue in a straight line until it hits something. In the external frame of reference, that is. If we spin our camera again, we see that in the room's rotating frame of reference, the ball is following a curved path as soon as it leaves the thrower's hand. The thrower gives the ball a high speed that would easily overcome the centrifugal force, take it right through the center of the room, and smack it into the wall on the far side. But high speed only makes the Coriolis force stronger. So the ball is immediately deflected to the right, and it never even makes it to the center of the room. In plans to use rotating environments for artificial gravity in outer space, it is the centrifugal force that gives us what we want. But the Coriolis force is unwanted in this application. Coriolis forces make it difficult to move and work because your limbs and your body's center of mass are deflected in ways that you're not used to. Furthermore, your inner ear is affected, causing dizziness and severe motion sickness when you move your head. Yet another problem is that the centrifugal force can be much lower at your head than at your feet. All of these problems might be solved in one of two ways. The first is adaptation. Humans are very adaptable animals and may be able to overcome these problems with continued exposure. The second is simply to make the radius of rotation much longer. In that case, you don't have to spin as fast to get the same centrifugal force at the edge, so the Coriolis force can be much weaker. Also, the centrifugal force will not change as much over the length of your body. I hope this has helped you gain a deeper understanding of rotating environments and why I think they're so nifty.